All right, so interactive servo loop tuning is the section we'll be covering until lunch and probably a little bit after lunch. And interactive servo loop tuning basically comprises modifying what we call servo loop gains to minimize a quantity called following error. A laser pointer up here. Following error is typically denoted by E of t, where E represents the error and t is a time variable. And that is the difference between commanded motor position, R of t, and actual motor position. In other words, it's the difference between where you want your motor to be and where your motor currently is. So we use two test trajectories to modify all of the gains in PMAX servo loop to achieve a minimal E of t or following error. The basic parameters we'll be modifying are all listed here, and they fall under the structure tree motorx.servo. The first gain is Kp, also known as the proportional gain. The proportional gain is proportional to the closed loop natural frequency of your system. So if you want a faster response or a stiffer servo, then you will need a higher proportional gain. Next is the derivative gain, KVFB, also known in the literature as Kd. This acts as an opposition force or a damping force proportional to the speed of your motor. So basically we want to add Kp until we have the natural frequency we desire, and then add KVFB to damp out unsafe oscillations. And you'll see some examples of that when I show you plots. Velocity feed forward is servo.kvff. This is intended to eliminate falling error at constant velocity. Integral gain, Ki, is basically acting on a sum of errors over time. Ki is necessary when you have significant body forces present on your system, such as inherent friction or gravity. For example, in a vertical axis, you have to have Ki or it won't work well. An analogy we like to use is when you're driving with really bad alignment, your car is always pulling to the left, your brain naturally tells your body to pull to the right the same amount. That's the same thing integral's doing. It detects a force on your system active all the time and basically just deletes it by summing the error over time and then multiplying by the integral gain. Next parameter is the integration mode, SWZVint. This allows you to tell PMAC whether to integrate all the time throughout your trajectory or just at the end of the move when the desired velocity is 0. Next is acceleration feed forward, KAFF. This helps to eliminate inertial lag and tracking at constant acceleration. And lastly is the friction feed forward, KFFF, which helps you to break free of stiction. This is really helpful for older motors that might stick when you start to move them, and piezoelectric motors which have an inherent stiction that's pretty significant at the start of a move. So generally we recommend using friction feed forward for those kinds of axes. And note that whenever you're doing the interactive tuning, you need to have the load connected to your motor because the load will significantly change the required tuning gains to get the bandwidth that you want. So just a few steps are required to actually do the interactive tuning, and you don't need necessarily a background in controls to do it, but it does help to understand some of the physical meaning behind these gains. So first we need to consider the setting of the integration mode, servo.swzvint. While you are tuning the step move, you should set this equal to 0. That way your position error integration is always active, and you can see the effective Ki term more easily. And then when you switch to the parabolic move to tune your feed forward gains, you want to set swzvint equal to 1 so that Ki does not influence the shape of the plot. And then once you've finished all of your tuning, you should generally just turn SWZV int back to 0 so that your position error is always being integrated. So the first test trajectory we use to tune the gains is the step response. I'll show you where that is in the IDE in just a moment. And then in the step response, you tune in this order, KP, KVFB, and then KI. So the idea is we'll increase KP until we overshoot and oscillate around the step target. Then you increase KVFB until we damp out the oscillations so that there's no overshoot. And then lastly, you add KI if necessary in order to achieve zero steady state error. A nice property of KI is that it virtually guarantees zero steady state error if you add even just a little bit, but you don't always need it. After you finish these gains, you can move on to the parabolic move, and then you tune in this order, KVFF, then KAFF, and then KFFF. So a good starting place for KVFF is actually to set it directly equal to KVFB, and then after that you only need to change it a little bit. Lastly, to note, if you're using a velocity mode amplifier, then you just set all of the derivative gain terms equal to 0, so KVFB and KVFF. That's because your amplifier will actually be closing the velocity loop for you. So any questions on the procedure before I show you some handy diagrams? Okay. All right, so the interactive tuning window can be found in the IDE by clicking Tools and then Tune. So please do that now. And then go to the Position Loop Interactive Tuning tab, and that's where we'll be spending the next hour and a half or so. And the first test trajectory is under the Step tab right here, where I have highlighted. Under the Step tab, we have two parameters, step size and step time. The step size generally wants to be 1/4 to 1/2 the revolution of the motor, or 1/4 to 1/2, that's for a rotary motor, or 1/4 to 1/2 of a commutation cycle for a linear motor. And then the step size, or the step time, simply has to do with the bandwidth of your system. If you have a really light load, responsive motor, you can have a smaller step time. If you have a really heavy load and you think it'll take a long time to settle, then you can increase the step time. The second move type we will use is parabolic velocity. The tab is parabolic vel period. And here we have another move size and move time. And here you want to try to emulate the most difficult kind of move you think your system will need to experience. So if you need to, for example, move 1 meter in half a second, you can figure out how many counts represent your meter and then write that under move size in motor units, and your time would be 500 milliseconds. So if you tune to the most challenging move you expect your system to experience, then easier moves should be totally possible. So your step move will look like this diagram, where we have an instantaneous commanded position that you specify in the move size. Then your motor will attempt to reach that target as quickly as possible, and then it goes back to the starting point of your move. So the vertical axis is commanded position, and the horizontal axis is time. So basically, as you're going through the tuning exercises, and then subsequently tuning your actual machines, you'll be modifying gains and then comparing the comparing the actual position response to these diagrams. So first, you want to increase KP and add a little bit of KVFB. You always need both. Increase KP until your actual position overshoots and oscillates around the target. Here in this diagram, the target is that dotted line. So our actual position is going over the dotted line, and then it's oscillating around it. Once you've achieved that, your Kp is probably sufficient, and you can just add kVFB so that the amplitude of the oscillation goes to 0, and you don't overshoot anymore, but you simply rise to the target and then stay at the target. Then you'll see something effectively like this. This is effectively the desired response, where you just go right up to the target and then remain at the target. If you see this kind of shape, it means you probably have too much damping from too much kVFB, and the response ends up being really slow, and you might not even reach the target position in the amount of time that you've given it. In that case, you want to either increase Kp or decrease kVFB so that it's less damped. If you have a constant position offset, it could be a number of things. It could be you forgot to do the DAC calibration for your motor, so that you have a constant amount of voltage applied to the motor that you don't want. It could also be you don't have enough Kp, so that you're not giving enough stiffness to the motor for it to reach the target, and it just gets stuck because of friction before it reaches the target. And it could also be you have a body force, such as friction or gravity, and you need to add Ki to eliminate that. And as you add Ki or Kp, whatever you need, this flat spot should approach the target. So once you've finished Kp, kVFB, and Ki, you can move on to the parabolic velocity move. But something you need to pay attention to in the step move first is the servo command. So if you look in your tuning window under the step move, you see that the right axis should be servo command. If it's not on your system, then change it to servo command. You see right here, the bottom right corner of the tuning page, make sure the right axis is servo command. And that way, when you do a step move, you can see how much effort PMAC is putting out to achieve the actual position that you want. So the servo command shows up in yellow, and if you see in your servo command a flat spot at any point in the trajectory, it means you're actually saturating the output of your motor, as specified by the I2T protection settings. So the saturation is indicated by these little circles here. This means that adding Kp past this point won't help you at all, because you're already commanding the maximum amount that is safely allowable for your motor. That amount is dictated by max DAC, which is a motor structure, motorx.max DAC. So at that point, adding Kp won't fix your problems. You need to do something else to fix the tuning of motor. Perhaps decrease the step size. Maybe you're doing too intensive a step for your motor to actually achieve, and you can back off a little bit. So next is the parabolic velocity tuning. Parabolic velocity moves command a velocity profile of this shape. It's not quite sinusoidal, but it is parabolic, and your motor's velocity will attempt to follow that shape as well. And of course, the derivative of that profile will be a downward pointing triangle, and that is the acceleration profile. So the process of tuning the feed-forward gains comprises comparing your motor's following error to the shape of both the velocity and the acceleration profiles. And I just want to reiterate, a really good place to start kVFF is to set it equal to kVFB. Then you only have to change it a bit from there. So if you see that your following error is highly correlated with the velocity profile, in other words, the following error is right on top of the velocity profile, you need to increase kVFF. And as you increase kVFF, velocity here and time here. Our initial falling error looks like that, and as we increase kVFF, the amplitude should decrease like this until ultimately you have just a flat line, assuming there's no other changes you need to make. If you see that your falling error is highly correlated with acceleration, in other words, your falling error looks like a downward pointing triangle also, you have some inertial lag in your system, and you need to increase KAFF to get rid of that. So as you increase KAFF, your initial falling error shape will decrease in amplitude as well. So the tip of this triangle should come closer to 0 as you add more KAFF until finally you just have a flat spot. If you have this case where you have a completely flat spot and then a sharp transition and then another flat spot of equal magnitude but opposite sign, then you have friction in your system and you should add KFFF. So as you add KFFF, this flat spot will come up towards 0, that flat spot will come down towards 0 until you have minimal falling error. Now if you see this case where you have mostly an excellent looking falling error profile, except for a big spike in the beginning and the middle, that's about as good as you're going to get, and you've probably reached the physical system limitation. So you can experiment with deadband a little bit. I think Sercon probably talked about deadband, but generally that's about as good as you're going to get, and you can either settle there or maybe decrease the difficulty of the move that you're doing. So if you see the inverse of the profiles that I just showed you, like here, we see that the falling error is reflected from the velocity. Normally the velocity profile looks like that, but our falling error profile is reflected like that. It means you have too much velocity feed forward. You've actually inverted your falling error, and you need to decrease your velocity feed forward to bring this peak up, this peak down. If you see this case where you have an upward pointing triangle, you've added too much KAFF, and you need to decrease it to bring the tip of this triangle closer to 0, and these two tips up to 0 also. If you see this case where you have basically a rounded spot, sharp vertical transition, and then another rounded spot, you have a combination of damping and friction. And you want to first increase KVFF until these rounded parts come up and become flat spots. Both of these rounded spots will flatten out. Once you've achieved that, you simply need to increase KFFF to eliminate the friction effect, and it will bring these two sides back up, closer to 0. You can sort of visualize it by superimposing these two conditions on top of one another. If I added this to that, you would have essentially this square wave shape, but with rounded portions. So if you just eliminate the rounded portions, all you have is this case, which can be eliminated with friction feed forward to bring those parts close to 0. And very similarly, this guy is a combination of inertial lag and friction. So you can visualize by adding this case to this case, you would have basically this ramped spot right here, and this ramped spot right here, which is exactly what we have. So as you increase KAFF, the ramps will flatten out on each side, and then add KFFF to bring the flat spots back to 0, just like the friction case. So don't be intimidated. This just takes a little practice, and with like an hour, you guys will feel much better. You can sort of treat it like a video game. You know, you get better at tuning certain gains and everything, and then it's kind of fun. And just for your reference, here's some relative magnitudes for these particular motors. Of course, the gains you will need depends on your motor and your feedback resolution. So you can take a look at page 144 for kind of a starting point. And just to note, there are alternative feedback gains. Alternative feedback derivative gains. Instead of KVFB, you can use KVIFB if you want better disturbance rejection rather than trajectory tracking. That's simply because this is added to the input of the integrator rather than the output of the integrator. So the integrator is acting on velocity error rather than position error. And velocity error always tends to have more noticeable higher frequency components. So if you have a lot of disturbances going on, a lot of like objects hitting your machine randomly, or a lot of unpredictable problems along your motion, you can use that instead. And if you use KVIFB, you should also use KVIFF, which is the replacement for KVFF, when you're using the disturbance rejection gains instead. They always need to be used in tandem, and you should not mix and match the two different types of gains. So just to give you an idea of the desired results here, for your step move, we want to aim for a trajectory that looks kind of like this. You have your position. Here's your target. So you want to come up to the target and then come right over. So here's 0% overshoot, 0 steady state error, and you want a natural frequency of approximately 20 hertz. And you can use any of the motors in your system to do this, 1 through 4. You'll probably get better performance from motors 2 and 3, the brushless motors, just because brushless motors are generally way better than brush motors. And then for your parabolic velocity move, if you have this commanded velocity, you should try to just have a falling error that is centered around 0 with an amplitude less than 10 counts. The best I've ever seen somebody get is like 1.6 counts with these particular motors, so if you can get that, good for you. That's a great accomplishment. I think the best I can do is about 2 counts, so there's a challenge for you. All right, so for demonstration purposes, I'm going to actually set all of my gains to 0 to start with. And I will leave my fatal falling error limit alone and the servo output limit alone as well. Are you rolling, Alonzo? Or? Okay, cool. Excuse me. So like before, I want to keep my step size between 1/4 and 1/2 of a revolution of the motor. So these particular motors have 2,000 counts per revolution on their encoder, so 1,000 counts is just fine. And then I will start with a fairly conservative value of 5 on KP. This is close to the default gains. And then, generally speaking, you can do something like between 5 and 10 times the KP for your KVFB, and then I will do a step move and see where we're at. So generally speaking, you always want to start with some KP and some KVFB. If you have no KP, the motor won't move. If you have no KVFB, the motor will be out of control and oscillating, depending on how much friction you have in the system. So in this particular case, we can see a couple of problems. We can see that I'm actually overshooting the target. The target is this pink line, command position, and then I'm stopping at a target other than the pink line. That means I didn't have enough Kp to actually oscillate around the target. So I want to increase Kp until I am centered around that target. And then you can also see I'm oscillating quite badly. So I overshoot the target by a good amount. You can actually see at the bottom of the screen, it shows you how much you overshoot, shows you your natural frequency, shows how long to settle until you stop moving and so forth. And I have just stupid amounts of overshoot. So I want to add KVFB also to get rid of that. So first I want to increase Kp a good amount. Let's try doubling it first. And then at the same time, I'll double my KVFB to maintain stability. Here we're getting a little bit closer. You can see that the gap between my final resting position and my commanded position is getting a little bit smaller. So keep increasing Kp until we're actually centered around the target. And at the same time, increase KVFB to maintain stability. Now that gap is getting smaller and smaller compared to before. So just continue iterating the process of increasing Kp and KVFB. The gap continues to shrink. Now that gap is almost totally gone, so I'll just keep increasing Kp until the gap between the resting actual position and the servo command is gone. Let's do large jump. Now there's almost no gap, so just increase a little bit more. But you saw that there was a large overshoot. So I increased KVFB to eliminate that. And now we're at the point where there is virtually no gap. There's still a very small gap, but there's virtually no gap between the resting actual position and the commanded position. But the main problem is we have an enormous overshoot peak, which is for some applications acceptable, for some applications unacceptable. It really just depends on your scenario. And my natural frequency, you can see at the bottom there, is above 20 hertz. So I've achieved the criterion that I gave you guys for the natural frequency. Now we just need to damp out the overshoot and get rid of that steady state error. So to damp out the overshoot, I will increase KVFB by 1000. Now you can see that that overshoot peak is completely gone. And probably added a little bit too much KVFB. So you can see the value we want is between 2200 and 2500 because I have a little peak here at 2200 and it was too damped at 2500. So I'll try 2400. And now we have a pretty nice looking response. This slight difference between the settled actual position and the commanded position could be due to a DAC offset that should be eliminated during the motor setup process or a small amount of Ki. So add a conservative amount of Ki first. A good number to start with is 0.001 in general, because Ki can destabilize the system really quickly. So its magnitudes are generally much smaller than the other gains. And you can see that just adding a teeny bit of Ki has completely eliminated the steady state error on the return very quickly and a little bit more slowly on the rise. Whoops, accidentally closed the screen. So depending on your application, this could be a desirable response. You could toy with it a little bit to perhaps bring this initial peak down a little bit. I still have a 1% overshoot, which you could tinker with to get rid of, but I won't bore you with the process. And now this looks good enough to move on to the parabolic velocity move. So clicking on parabolic velocity, I will first set kVFF equal to kVFB. Like I mentioned a couple times, that is a good place to start, and then right after doing that, I will issue the parabolic velocity move to see where we're at.